The next topic that we'll cover is this notion of confidence intervals. So, confidence intervals are extremely important for validating estimation. So, you can think of confidence intervals as a way to validate estimation. Okay, so far we've looked at estimators for estimating various parameters of a distribution given samples. And now, how do you know if an estimate is good? Okay, so that's the notion. That's what confidence intervals tries to do. Okay, so we'll start off with a few definitions. We'll talk about a bunch of trade-offs, and we'll talk. So today we will look at a general technique to come up with confidence intervals. So this technique will be general, but it will also be weaker than what is best possible. Okay, and then we will delve into this specific example of Gaussians when you know the variance, in fact. And this gives much tighter estimates than so you can view these as like technique 1. So technique 1 gives like a rough way of coming up with confidence intervals, but it's very general. And technique 2, which is more involved computation, we will use it in the example of a Gaussian. Okay, so let's start off with the quick definitions. So what are confidence intervals? Right, so let's start with the formal definition. Okay, so a confidence interval consists of two estimators. There's a pair of estimators. Let's call them L and U. Okay, so recall that we are in the same setup as we have before. So we have some unknown, we have some distribution D from which you get samples x1 through xn, and these are all IID. Okay. And this distribution has parameters. It has a bunch of parameters, and we are interested in one parameter which we call theta. Okay, and this is the parameter that is currently of interest. Okay, so when we have multiple parameters, we can talk about such confidence intervals for for each of these parameters. Okay, so confidence interval is a pair of estimators L and U. So these are functions of x1 through xn. xn such that the probability that the theta belongs to this interval Lu is pretty large. Okay. So it's 1 minus alpha. Okay, so confidence intervals are parameterized by this parameter alpha. So confidence interval of alpha, okay, is a pair of estimators L and U such that the probability that theta is between these two. So we write L and U to say it's a lower bound and an upper bound. Right, so L is like the lower bound, lower estimate, and U is the upper estimate. Okay, and we say that, and what we need is a property that the parameter of interest, which is theta, should lie between the lower and upper estimates with a pretty high probability, with at least 1 minus alpha. Okay, and typically we think of alpha as alpha equals 0.05. Okay, so that's a typical value of alpha that people use in statistics. Okay, so you're 95% confident that your parameter of interest lies in this interval L comma U. Okay. So that's the formal definition of estimators. Okay, so let me give a quick example. Okay, so at least an intuitive example, and which could act as like a motivation. Example slash motivation. Okay, so suppose we have a Bernoulli random variable. Okay, so this takes value 0 or 1, and 1 is taken with probability p. And now let's say we have observations x1 through x100 of this Bernoulli random variable of Bernoulli of p, and suppose that 50 of these 100 are ones and the rest are zeros. Okay, so now of course what we've seen last time is that an estimator for p is 1/2, right? So we saw that the number of ones divided by the total number of samples is an unbiased estimator. So this is what we saw last class for the value of p. So in this case, that estimate is exactly equal to p equals half. Okay, and we also saw this notion that if you are looking for the maximum likelihood, the p which is most likely to produce observations that satisfy this property, then p equals half is like the best value. Okay, so this was the idea behind the maximum likelihood estimator. Okay, but now the question we are trying to ask is, how confident are we that p is half or p is kind of close to half? Okay, now that's the intuitive question we are trying to ask. Okay, and the first question you might like to ask is, how confident are we that p is equal to half? Okay, and note right away that this question does not make sense, because imagine p is equal to, okay, why? So imagine p equals 0.500001. Now it's you really cannot tell the difference using 100 samples between p equals half and p equals 0.500001, right? Because so even if you had p equals this value, it's pretty likely that 50 of the 100 are ones. Okay, so asking if we are confident that p is equal to a certain value does not make sense. Okay, but now consider the modified question. Okay, so how confident are we that p belongs to, let's say, 0.25 and 0.75? Okay, so p lies between 1/4 and 3/4. Now you can imagine that this answer is actually really high, right? So because you've had 100 samples, and if p, the guess would be that we should be really confident. We should be right, because if p is, let's say, less than 0.25 or p is more than 0.75, then seeing 50 heads is super unlikely, right? So seeing 50 heads is very unlikely. Okay, so that's so this is what we want to formalize. Okay, and this is what this notion of an upper and lower estimate try to quantify. Okay. All right, so this is the notion of and actually, yeah, before I move away from this example, so what we'll do in the next lecture is try to actually give a number to terms like this. Okay, so we should be very confident that this is true. So in the case of Bernoulli, we will come up with like a nice estimate in the next lecture. Today we'll look at it in general for other distribution. I mean, in general for all distributions. Okay, so that's the goal behind confidence intervals. Okay. So let us now see the next thing, which is how do you try to obtain confidence intervals. Okay, in the next video.